folks. Wanted to wrap up a few things related to functional programming, a few odds and ends. And I thought it would be interesting to think about patterns of recursion. So we have been looking at one pattern of recursion, which is called tail recursion. And tail recursion has two primary attributes. One is that it's basically stackless. And the second thing is that there's no branching. And the third thing is that the memory is carried along. The memory is carried by parameters. And that allows it to be stackless. Okay, so that's the idea of tail recursion. Now, if you were to write a tail recursive solution to a problem, you might find that tail recursive solution is a little more complex than a general recursion solution. So a general recursive solution does use the stack, and it may have branching. So is this it? You have general recursion or tail recursion when you're looking at recursive solutions, and it turns out not really. There's some specialized forms of recursion that I would say are subsets of general recursion for you just to be aware of. They're like patterns of recursion. And so one of those is the every pattern. I guess I'm not going to put it in quotes because I underlined other things. So the every pattern. So you already know about the every pattern because we've talked about, as an example. Okay, I'll just define it and then we'll do an example. So an action is performed on every item in a list. So an example of this might be apply all. So we did this function a little bit earlier, and the way apply all worked is you would say something like apply all cube, and then a list like 1, 2, 3. And the result of that would be a new list with 1 cubed, 2 cubed, and 3 cubed. All right. So that's an example of the every pattern. I don't want to rewrite the code for that, but you get the idea. But it can show up in lots of different ways. And it's a thing to think about. It's like if you want to do recursion and you have a list, do you want to do some operation on every element of the list? So that's one pattern. Another pattern is called the keep pattern. And it's like every, but with a filter. So what the keep pattern does is it says, I'd like to keep I'll do that in lowercase. So you might, whoops, ugh, don't want to do that. Okay, so what you'd say is something like this. So this is an example. You might say something like keep 3, and then something like this: 1, 2, 3, 4, 5, 6. So there's my list. And what keep 3 does is it will return a list, but only a list with strings that have 3 characters or less. All right. So let's take a look at we'll write the code for that because we haven't really talked about string manipulation. So we're going to have this, this, and this returned. And so the end result will be a list that has 1, 2, and 6. All right. So it is similar to every because keep applies to every element in the list, but we're just extracting or filtering to create a reduced list based on some pattern. So this keep 3 is code we're going to have to write, so let's write it. All right. So define keep 3 and keep 3 is going to take an argument, and that argument is going to be a list. All right, and so I love using cond, so we're going to use cond. And we're going to say if the list is empty, then we'll return the empty list. All right, so cond empty, return empty list, return the empty list. Okay. All right. Now, the next thing we're going to do is we're going to say, think about the recursive case. So the recursive case is going to be if equals 3, and now we're going to go and we're going to extract the first element in the list that we're processing, and we're going to see what the string length of that is, the size of that is. So that is, there's a function called string length. That's a dash. And if we take the item from the list, like let's say we're processing the list so far and we're processing list number 1 or item number 1. All right, so the way we're going to do this is we're going to say if this string length of the symbol string, and what symbol string does is it takes an atom, so for example 1, and 1 is considered an atom, but we can convert 1 from an atom to a string by saying symbol string. All right, so symbol string of first of list. So whatever the list is that we're processing right now, and if we assume this is the first time in, we would be processing this list here. The first of list is going to be this item. We're going to convert it to a string using symbol string, and then we're going to get the string length of it. And it turns out that is going to be 3. All right. So if this is true, whoops. If this is true, then what we're going to do, we're running out of space, so I'm going to go on the next line. If this is true, then what I'm going to return is a list that I'm going to build up using the following. The first of L, this thing that we just extracted and determined had a size of 3. And then I'm going to recursively call keep3 on the rest of the list. Okay, so that's our really powerful recursive, one of our really powerful recursive statements. So this one is going to get executed when the list has a list item has a string length of 3. But what happens if we're in a situation where that's not true? We've got a list item, for example, 3, that has a size that's not 3, which is pretty funny, right? 3 does not have a size of 3. Okay, so what do we do here? Well, I'm going to say else. What we're going to do is we're going to call keep3 with the rest of the list. All right. And that way we keep things moving along. All right. So this is going to build up really nicely, and I'll end my cond here down here, and I'll end my define down here. All right. So now we have a string operation. Let's take a look. Why don't we do a trace just to see how it operates? So let's see. I guess I can do it up. I've got a little bit of space up here. So we're going to start out with the list being. I'll tell you what. You have that in your notes. So I'm going to do this. I'm going to grab this list, and we'll just talk about what happens to the list. Oops, I lost control of my pen here for a second, so I got to give it a little bit of a reminder. Okay, hopefully that worked. Yeah, usually it does. Okay, so we'll grab this list. Actually, we'll just take this whole thing, and then we can look at what the calls look like. All right, so we'll copy that, bring that down here. And okay, so this is the initial call. So the initial call is going to, I'm going to clean this up a little bit too. So just so we can see what we're talking about here. Okay, 1, 2, 3, 4, 5, 6. Okay, so that's our initial call to keep. Now, it's not empty. And what we're going to do is we're then going to take a look at the first, we're going to take a look at the string length of the first thing in the list. And that is going to be 1. And that is going to have a string length of 3. And so what we're going to do is we're going to do a cons of 1. Whoops. We're going to do a cons of 1 with a new call to keep 3. And that is going to be the rest of the list. So we'll copy this. Whoops. Copy. And we'll paste it right here. And I'm going to just do a little bit of shrinking it a little bit and just a little bit of editing, because now we are not going to have a 1 in it. Okay, so we're going to call it with 2, 3, 4, 5, 6. The same thing's going to happen. We're going to hit that empty list. It's not empty. We're going to check to see if the first item in the list has a size of 3, which it does. And so we're going to do a cons again. And this time we're going to do a cons, whoops, that's the French version of cons. Cons of, 2 with keep 3 of, and we're going to grab the 3, 4, 5, and 6. Whoa, shrunk it down there a bit. Okay. All right. Now we're going to repeat the process. It's not empty. We're going to look at 3, and we're going to say, hey, 3, does that have a string length of 3? Nope. It has a string length of 5. So that second check isn't going to work. And so we're going to hit the else. All right. And so the else says, to find out what keep 3 of this list is going to be, you need to do keep 3 of the rest of the list. All right, which means we're going to do keep 3 of the rest of the list. 4, 5, 6. All right, so we're going to check, is that empty? Nope. Is the first element in the list have a size of 3? Nope. And so to resolve that, we're going to do keep 3 of the rest of the list. 5, 6. And that one also, the first element is not 3. So we're going to do keep 3 again of the rest of the list. This one is 3, so we're going to do a cons of 6 with keep 3 and an empty list. Now, when we have an empty list, what keep 3 does is it returns, keep 3 is going to return an empty list as a result. And that's really important because cons expects an atom and that as one argument and a list as the second argument. So we return this empty list, and then we build up this empty list using the cons operations that have to be completed. Now, all of this stuff is sitting on the stack, so we are using stack to get this done. But then we end up with a final result of 6 inserted into the list, 2 inserted into the list, and 1 inserted into the list as the list gets passed back and the calls to keep 3 get unraveled. All right, and so we end up with a final result of 1, 2, 6. All right, so let's just review. We were just talking about an interesting recursive pattern called the keep pattern. And the way the keep pattern works is you basically put some kind of filter on a list that's being passed in, and you decide what are you going to keep in the list and what are you going to throw out. All right, and so I just gave you an example of a keep pattern, which is called keep 3, and it's just arbitrary. It just says, hey, on this list, we're only going to keep the strings that have, or the atoms that have 3 elements. Okay, so there is one more pattern, which is called the accumulate pattern. And my pen died again. Wonder if I've just been using it so much, it just needs some extended battery life. In fact, you know what? I think you know me well enough to know that I'm a little bit forgetful. And so I tend to misplace things. And I misplaced my very expensive Apple Pen. And as a result, I had to go out and buy another one. It's like $100. And I ended up finding the Apple Pen underneath the seat of my car. So now I have 2 Apple Pens, and I have them charged up one of them's charged up and the other one's not. So I'm going to use this one that's charged up. Okay, so let's talk about the accumulate pattern. I have company. My dog just came in. She doesn't like it when I'm sitting on the bed doing lectures. That's where I do my lectures because she likes to have the whole bed to herself. And believe me, she is like a little princess because this bed is a king size bed. So I don't understand what her problem is. But anyway, she just refused to get up on it when I'm on here. Okay. So how does the accumulate pattern work? Well, the accumulate pattern is like the every pattern, but there's a single result. All right. So, so basically, what we're going to do here is we're going to, it's a single result without cons, because cons, the every pattern and the the keep pattern that we just looked at, they both produce a result. In fact, every function you call always produces some kind of result. But what we're talking about here is taking a list and then combining the elements in the list in some way so that you end up with it basically like a single atom or single value as your result. That's really what's going on here in the accumulate pattern. All right, so let's define, well, let's take an example. Let's create a function called atom. All right, it's kind of snarky, and it takes in a list like 1, 2, 3, and what it does is it adds up the elements of the list. So the result that gets returned is 6. All right, the sum of the elements in the list. All right. So how does this work? Well, let's write the code for it. Define atom list. All right, and here's my friend cond. Cond! All right, and what we're going to do is we're going to say if we have an empty list, we're done with the list, we're going to return the value of 0. All right, and otherwise, we are going to take the first element in the list, it's not list, it's LIS, the first element in the list, and we're going to add that to a recursive call to atom with the rest of the list. All right, and that's pretty much it. So let's do a trace of the execution of this. Push this up just a little bit. I think we'll have room. So if I say atom 1, 2, 3, what's going to happen is we're going to check first, is this empty? Nope. All right, here's what we're going to do. We're going to add up the first element of the list, which is 1, plus a call to atom with the rest of the list, which is 2, 3. All right, that's going to be, when we call this again, is it empty? Nope. So we're going to add the first element in the list, that's 2, and we're going to add that to atom of the list that just contains 3. So that's going to result in 3 with an atom and an empty list. And that is going to return 0. So then that 0 gets added to the 3, which produces 3. That is going to be returned to the 2. So let's just do this. So the 0 plus 3, that means this is going to yield a 3. That 3 is going to be returned here. The 2 plus 3, that's going to give us 5. That's going to be returned here. And the 1 plus 5, that's going to give us 6. And so our final result is a 6. So we're taking the list, collapsing it, not using cons and returning lots of things. And we're just finding some way to accumulate based on the atoms that are in the list. So that's another pattern. Okay, we have one more pattern that I want to talk about called backtracking, but I'm going to set up a separate lecture for that.